Alright guys, so we're going to finish up section 7.4. Today we're going to move into logistic models. So in the 1980s, many people were alarmed by the rapid growth rate of AIDS. The figure 717 right here contains data from a report by the Global AIDS Policy Commission showing the increase of AIDS cases in North America from 1985 to 1991. Looking at the graph in 717, it might appear that it was an exponential pattern. But if you look at the table, there's a decrease in the rate of growth from year to year. Okay? It's not the same though. Okay? Thus, an exponential model is not appropriate to model this data. Okay? So, let's do some highlighting. Oh no, I left my pen open again. So, oh no. Let's see if I can find me another one. Okay, so looking at the graph in figure 717, it might appear, and I thought I found another one, but that one's dry too. We're trying here. Let's try one more pen. If not, then I have to switch colors. Alright, let's give this one a shot and see where it takes us. The growth rate of, oh, that definitely is not good. That was following an exponential pattern. As we see in the following table, and like our earlier bank account example, the growth rate is not the same from year to year. Okay? An exponential model is not appropriate to model the data. So we need to introduce another type of model. So we've had linear, we've had quadratic, we've had exponential. So in studying the growth of populations, demographers often use a logistics model. A logistics model takes into account the fact that as the population grows, there are limits in terms of space, food, and so on to prevent the population from following a true exponential growth pattern. So remember what we always did. We did 1 plus the rate times the original amount for exponential. So we're just mainly highlighting on these pages right here. So we would want 1 plus the growth rate times the population at the end of the previous year. So it changes every year. So I'm going to put a little block here because I'm not going to color this whole thing. In both cases, we assume that the money in the bank account and the population will grow at the same rate from year to year. However, with restrictions on the amount of food, water, and space, and so on, any environment can sustain only a limited population. As the population grows, the percentage of this capacity that has been used up influences the rate of growth. If a population has a growth rate of 3% in the beginning, it's reasonable to multiply the existing size of the population by 1 plus 0.03, because that's our exponential growth, to estimate the population the next year. However, as the capacity to sustain further population diminishes, we must reduce the growth rate accordingly. So, in a logistic model, it's common to represent the maximum capacity that the environment can support by 1 or 100%. We will define a quantity P of N that represents the percentage of the maximum capacity that has been attained by the population in year N. So if we want in year 3, this would be P of 3 instead of, P of N. For example, let's say P of 5 equals 0.40, means that at end of year 5, the population we are studying has attained 40% of its maximum capacity. If this same population had original growth rate of 0.03 to calculate P of 6, we would reduce this growth rate by a factor of 1 minus P of 5, which equals 0.60 because we would do 1 minus the previous year's amounts to get a growth rate of 0.018 as shown in the following diagram. So you do 0.03, which is the original growth rate, times 1 minus the previous year's. Okay? So we would get this. Okay, so your logistic model is to get the next year, you do 1 plus the original growth rate minus the previous year's capacity times that number, like we did just here. Okay, so it simplifies once you do that to that. So let's do some problems. Okay, this will make more sense when we actually do problems. Okay, assume that the population is growing initially at a rate of 3%. So this is the original rate. So R is 0.03. Also assume that at the end of the 5th year, the population is at 40%, okay, of its maximum size. So that means that P of 5 is 0.40. Okay, P of 5 is 0.40. At what percentage of its maximum size will the population be 1 year later? Okay, so remember, to find P of 6, you're going to take 1 plus the R, then multiply that times 1 minus the previous year, so that would be our P of 5. Then you're going to multiply what you get here by that P of 5. Okay, so let's plug in some numbers. So we have 1 plus 0.03, open parentheses, 1 minus 0.40 times 0.40. Okay, so if I've got 40%, then that leaves me with 60%. So that's 1 plus 0.03 times 0.60 equals 0.40. And it really helps us out that they had those same numbers right there. So we're going to have 1 plus 0.018 times 0.40. So this is 1.018 times 0.40. So we'll get out our calculator here. And what we're going to get is 0.4072, which means we will be at 40.72% capacity at year 6. Okay? And that's all you have to do there. All right? So that's that one. All right, moving on to the next page, last page. So notice in example 4, we did not compute P of 6 by substituting 6 in the sum equation as we did in previous models. Instead, we describe P of 6 in terms of P of 5. if we had not been given P of 5 explicitly, then we would have had to calculate it by finding P of 4. Okay? But to find P of 4 would require knowing P of 3 and so on. Okay? An equation that is defined so that you have to find a given value, so that to find a given value requires knowing previous values, is called a recursive equation. Okay, so that's what we're going to be doing with this next one. Okay, because they're not going to tell us the previous year. So we got to go all the way back to the beginning and calculate up to what we need. Okay, so biologists have chosen a nearly extinct type of lemur to populate a small island. They have introduced a number of lemurs that constitute 20% of the population of the island that the island is capable of supporting. Okay, so let's just note right here, they have introduced 20%. So this means that the original amount, P of O, is 0.20. Okay, if the growth rate of the lemur population is 10%, this means that R is 0.10, find what percentage of the maximum lemur population will be on the island in 3 years. So they want to know what is P of 3. Okay, so we know P of 0, so then we have to calculate P of 1. Then we'll know P of 1, so we'll have to calculate P of 2. And once we know P of 2, we'll be able to get that P of 3 that we want. Okay, so let's do these in different colors. So let's do P of 1 first. So the P of 1 formula is 1 plus R times 1 minus P of O, because you always do the 1 before it, okay, times P of O. So we have here 1 plus 0.10, open parentheses, 1 minus 0.2 times 0.2. Okay, so that gives me 1 plus 0.10 times 0.80 times 0.20. So this is now 1 plus 0.10 times 0.80 is 0.08. And I'm going to be your calculator to save us a little time. 1 plus 0.08 is 1.08 times 0.20. So P of 1 is 0.216. So if the first year it's 20% of the maximum it can hold, by the first year it's 21.6% of the maximum it could hold. Okay, so let's go to P2. Okay, so here we want 1 plus R, 1 minus P of 1 times P of 1. So here we go, 1 plus 0.10, 1 minus 0.216 times 0.216. Again, I'll be your calculator. 1 minus 0.216 is 0.784. Okay, if I multiply that by 0.10, I get 0.0784. So I have 1.0784 times 0.216. So P sub 2, so the second year, it's up to 23.3% of the maximum capacity. Okay, so it's growing. Then let's do P of 3. This is the year that they wanted. So this one, we're going to do 1 plus R times 1 minus P of 2 times P of 2. So this is 1 plus 0.10 times 1 minus 0.233 times the 0.233. So this is 1 plus 0.10 times 0.767 times 0.233. When I multiply 0.10 times this, I get 1 plus 0.0767 times 0.233. So I get 1.0767 times 0.233. And that's going to give me P of 3 equals 0.251. So it wants it as a percentage. So what they wanted was the percentage of maximum lemur population in 3 years is, and they want it in a percentage, so that's going to be 25.1%. And that is that. Okay. And that's all we have for that. So if you need to watch anything again, feel free to do that. If you have any questions, please feel free to reach out. And I hope you have a great day. Thanks.